Well, welcome everyone to geohug. So I'm just promoting you up as panelists. Please don't be shy. Come on through, get the cameras on, get the mics on. We have the lovely Quentin Masurel joining us today. But before we do get stuck in today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation. And I'd like to pay my respects to the elders past, present, and future. And yes, I'm super excited that we have Quentin Masurel joining us today. So Quentin is the Hammond Nisbet Fellow at UWA, where he undertakes frontier applied research integrating geoscience disciplines to help improve our predictive capacity and dedicate significant time to mentoring the next generation of geologists in the integration of field geology and structural geophysics. So the Yilgarn Craton of Western Australia is one of the key pieces of the Archean puzzle and one of Australia's most important mineral provinces. And today he'll be sharing insights on the 3-year-long research project from Yilgarn 2020, which was aimed at enhancing our ability to predict the distribution of mineralized camps. So this is going to be a fantastic session. I hope you all enjoy it. And yes, thank you so much, Quentin, for joining. It's awesome having you here.
My pleasure.
Before we do get stuck into your presentation, I was wondering what got you into geology to begin with.
Yeah, well, I'd like to say that, in fact, I wish I could say that it was a childhood dream, but the reality is a bit different. So I went to uni, everything, and I applied and I took a competitive exam to enter vet school. My grades were too low, so I failed miserably. And when you fail miserably in France, lucky you can actually go to the National School of Geology, which I did.
Really?
I've always loved rocks as well and mountain sports in general. But coming from the north of France, topography, picture like the climate, just like Great Britain, was not a reminder every day outside to just like get me to love rocks even more. So yeah, but I got there eventually.
I love that. That's so good. And what's been some standout sort of career highlights or some of your favorite geologic locations that you've been to?
I work mostly, almost exclusively on Precambrian terrains, like, in West Africa, a bit in Scandinavia. That's where I started with the masters. West Africa for my PhD and postdoc, and then the Yilgarn and a bit of Northern Australia as well. I say they're all phenomenal, but if I had to pick one in terms of the all added value, I think my years in West Africa was really eye-opening in terms of geology and also, the clash of culture, tradition, everything else as a package. So yeah, I really enjoyed my 10 years or 7 to 10 years in West Africa. That was really good.
That's awesome. And I do ask all my speakers to bring along some of their favorite pet rocks from their travels around. So I was wondering what you have for us today.
So I did manage to get one. It's actually from a PhD student at UWA that just completed his PhD working on the John D gold deposits, about 10 million ounces, in the northern Kalgoorlie-Konapi terrain in the Yilgarn Craton. It's quite a phenomenal rock. Like, not only it looks pretty good, but the thing you can see in this rock is actually 2 stages of gold. So there's a paper in Economic Geology, I think, that was released like a couple of months ago by Sumail. And in this rock, you've got 2 stages of gold. You've got, I think everybody can see, like if it's not too blurry, like those coliform, crustiform. In this case, the pre-crustiform, not so coliform. That's stage 1. That's what.
Can you lift it up a tiny bit? Sorry.
To the front a bit more.
Yeah, up higher a bit. Sorry. Yeah, there we go.
Yes, a beautiful rock with alteration in the wall rocks, but we're looking basically at the upper part of the rock. We've got the first stage of gold that is basically about like 1 gram per ton average and hosted as a fine pyrite grain within these coliform, crustiform veins. And then there's a second stage of gold that is actually just like all the little dark matrix or hydrothermal cements where the vein itself is brachiated. And that stuff could actually, from memory, run 3 to 10 grams per ton. And it's like fine quartz carbonate with a tiny acicular arsenopyrite and pyrite and base metal, like as sphalerite as well, like bits and pieces. So strongly encourage you to see Sumail's paper for all the details. I only picked the rock this morning from his office. He probably is not aware of it either. So yeah, good rock.
That's awesome. I love that. Well, thank you for sharing all that with us. And thank you so much again for being here. If you want to share your screen now and we'll jump straight in.
So thanks for the opportunity. It's actually, like I was saying to Jessica, it's a bit weird for me to be the other side of the screen on this one, but we'll go with it. So I'm supposed to talk to you about the tectonics and gold metallogeny of the Yilgarn Craton, and specifically the new or recent insight from the Yilgarn 2020 research project. So though I'm talking today, it could have been any member of the team. So I'm going to talk in the name of the full Yilgarn 2020 team that actually included some brilliant minds, PhD, master students, professors, postdoc at UWA, and our collaborators at JSWA. So let's roll with it. So just for those of you that are not familiar with the Yilgarn Craton, I'll start with setting up the scene a little bit. On the left-hand side, and I'll do the pointer. Screen, let me just get the pointer. Yeah, so it's been divided in about 7 terrains. So from west to east, the Naria, southwest, you and me. Then we get into the Kalgoorlie terrain, most famous for its phenomenal gold and nickel endowment, Cornell Pit terrain, and then as of more recently to the time at which this map was established, the Birdville terrain has been split into 2, Yarmana to the east and the Birdville terrain like further west. In terms of simplified geology, basically the Naria is probably the oldest building block of the Yilgarn. The southwest has been recently redefined by people at JSWA, but it's from the edges that we're starting to collect and get at, it's probably very old as well, potentially as old as the Naria. And then you've got the Birdville and the you and me that probably contain rocks between 3100 and 2720. And of course, what most people will know is the supracrustal rock sequences within the Kalgoorlie and Cornell Pit terrains, which are anything between 2720 and 2650. And there's so bits and pieces of those young packages in the Yarmana terrain and within the southwest terrain called the Saddleback Gridstone Belt. If I was to simplify and do a cross-section from northwest to southeast across the Yilgarn Craton, going from the margins here that are Paleoproterozoic, the Glenbourg terrain, and the Neoproterozoic Pinjar orogen, overlain by obviously the much younger Perth Basin. The section will look a bit like this, and that's based on a very simplified view on a couple seismic lines. So you'll get the northwestern margin of the Yilgarn that's quite complex due to obviously some of the younger Proterozoic orogens focused on the margin. Then you'll get to the you and me terrain, which is underlain by what we call the Archean seismic province. That in terms of its reflectivity is actually quite different from the upper to middle crust in the you and me, but seems quite akin to the Naria in terms of package or reflections as a whole. And then as you move to the eastern Goldfield super terrain, they're basically a series of terrain that have mostly been defined, I think, in terms of geophysics, and they're all bounded by a listric east-dipping crustal scale shear zone. That'll be important when I go through the presentations towards proposing a few geodynamic models. So we'll come back to this. In terms of geodynamic models, there's been a few models proposed, and I'm going to talk specifically about the time slice between 2720 and 2630 and the Eastern Goldfield superterrain. But as most often with Archean Craton, there's always 2 end members. One that involves mostly stagnant lead and plume-dominated tectonics, and the other end member that is obviously more uniformitarian in terms of model, and that involves the accretion of exotic terrains or magmatic arcs onto the margin of an older protocraton or older nucleus. And as in recent years, I think there's been a number of authors that actually just realized that it's potentially, at least in terms of the Yilgarn, hybrid model where plume or mantle upwelling of some side were involved and subduction was involved as well. Now, the issue we have when trying to test actually the proposed models is that we're dealing with Precambrian terrain. And on the top left-hand side, you've got a picture of what it looks like in the field when you step out there. This is a picture not too far from the Willona Township in the northern Kalgoorlie terrain. And I've had the chance to work in many other Precambrian locations worldwide, like West Africa, Scandinavian Shield, and the North Australian Craton. And it's pretty much the same story always, quite poor at crop conditions, thick weathering profiles, and if you're even more unlucky, then you've got strong vegetation or cover that prevents you from doing very detailed work and making connections between the stuff you see on surface. So lucky for us, we were able to set up a large collaborative crew and a project called the Yilgarn 2020 that was done in collaboration with a Geological Survey of Western Australia. It was sponsored by 7 industry sponsors with the logo listed up here and the names listed down here. It ran from May 2019 to 2022, and the overall objective of the project was to enhance our ability to predict the distribution of mineralized camps across scales. And lucky for us, we had 2 postdocs working full-time and 4 to 5 PhDs actually on the project. So what I'll do today is actually try to present you a bit of the key learnings. I won't go through everything. If you're interested to know the full story, there's a final report that just got released by MRIWA, should be available on the MRIWA website, but I'll take you through some of the key learnings of the project. And I'll also draw in some fantastic work by people at JSW that I think have really changed the vision as how we see the geodynamics and the metallogenic evolution of the Yilgarn recently. So just before I do that, in terms of core modules of the Yilgarn 2020, it was threefold. He included a module 1 that was looking at the composition and evolution of the Yilgarn lithosphere. Another one that went down in scale a little bit, that looked at understanding the camp scale architecture. And then zooming down even one notch more in scale, we had something looking at the petrochronological constraint and trying to develop new tools and workflows to map mineral fertility. So I get started with the composition and evolution of the lithosphere before I dig into time slices for the Yilgarn Craton. And if I were to summarize these 2 figures extracted from a recent paper by Archean, is that basically the Yilgarn can be seen roughly in 2 parts. There's a western side, which we call the western half of the Yilgarn, or the Yilgarn proto-craton, that is basically contains like a high Mg number in the range of 91 or so at a nominal depth of 100 kilometers. So something a bit more pristine to Archean lithosphere, whereas the eastern half is actually looks like a lot more refertilized with higher velocities, lower velocities compared to the higher velocities in the west. So a strong asymmetry between a proto-craton, older, more pristine Archean lithosphere, and something that is refertilized. Mostly, largely the timing of refertilization, though, it's still a matter of debate. It could be during the Neoarchean. It could be better candidate, I think, like can be found in the Proterozoic, and mostly linked to all these little square and polygons and diamonds in here. That actually the timing of refertilization as seen in carbonatite, kimberlites, and ultramafic non-porphyry today, roughly placed into the crust at 2060. And then some of the younger basins could be actually linked to the War Corner lip at around 1080. So a few possibilities, but this strong asymmetry is quite important. So now what I'll do is take you through a couple of time slices, and we're going to go from 310 or about, and hopefully go all the way down to 2610. So we're going to cover about 400 million years of the Yilgarn evolution. And I'll draw in a few data sets, including isotopes, geophysics, stratigraphic, geological. So we'll go for a little bit of the story. The reason why I start here is because I think we don't have all the cards in hand to say something really robust about anything that happened prior to that time slice, even though the story of the Yilgarn starts like way earlier than 310. So the first thing that happened for us today will be the Southern Cross supergroup and correlatives. So the Southern Cross supergroup has been defined in the western half of the Yilgarn, in the UNM terrain. The correlatives could happen and have been found in the Birdville terrain, for instance. So in terms of rock association, we've got basalt, andesite, dacite, rhyolite, volcanic rocks, plus and minus everything that is listed here. The curious thing or interesting thing is that most of the points here you see in terms of epsilon values versus age, despite the fact that there's protracted magmatism over about 100 million years, you can see that they stay within an error of true, mildly suprachondritic to subchondritic. So protracted mantle-derived magmatism of somehow over 100 million years. The geodynamic setting for this, many people have involved like plume and rifting, but I don't think we again know for certain. A lot more needs to be done in that space. In terms of a more visual, here on the left side, you've got the submarine neodymium data for all the felsic rocks available from the GeoView website as of 2021. On the right-hand side, you've got the spatial distribution of these rocks that are basically anything older than 2.9. And you can see that basically that's what Tim Ivanik at JSW call a horseshoe shape, where they're basically the oldest, obviously, like part of the Naya, and then we've got this beautiful distribution along most of the UNM terrain and the Birdville terrain, and they seem to be no distribution or no such rocks within the Kalgoorlie-Konalpi terrain and in the central part of the UNME terrain, which interestingly actually correlates with linear zones of anomalous juvenile magmatism, one which we refer here in the central UNME as the Q isotopic zone, and the one in the Eastern Goldfield superterranean that broadly correlates with the Kalgoorlie and Konalpi. I'll come back to that and why it's important. So jumping to the next time slice, 2820 to 2730, I forgot to mention that after 2900, actually, according to the available data, there seems to be a magmatic hiatus between 2900 to 2810. So something like in the order of 100 million years of tectonic quiescence, where the only thing that happens throughout the Yilgarn is actually the deposition of beef and quartzite. Now, from 2820 to 2730, we've got a second major magmatic event, which is correlated in the UNME terrain with the Murchison supergroup and correlatives to the rest of the Yilgarn Craton. And that's also a time where we emplace like nickel, copper, PG deposits. Now, in terms of the stratigraphic association, I think there's a thing that really changed the vision that we had about this. So it was argued like early on, like in the year 2000 and 2010s, that this episode 2820, 2730 was actually Plume related, but most of that was actually strongly linked to the geochemical signatures and the petrogenesis of these rocks. And Jack Lowry and collaborators at JSW actually changed the vision that we had, because we all assumed that they were true komatiite, but doing the work required in detail, it was actually able to show that the so-called true komatiites are in fact like platy, pyroxene spinifex textures and high Mg basalts. Now the implication is that we likely don't need a plume anymore. We could do a lot of other things because we don't need the high or elevated mantle temperature to generate true komatiites if we've got platy, pyroxene spinifex texture, high Mg basalt. On top of this rock, they also include like more black dolitic basalt, boninite-like rocks in association with low titanium basalt. There's also a few like calc-alkaline high Mg badar volcanic rocks, sanikitoids, hornblende-rich gabbros, so hydroslate, mafic magmas, and transitional TTGs. Now, I'll sum up like a lot of papers for you, but I think all the recent papers that looked at the petrogenesis of this rock association would agree that it's consistent with a Bakar-Krips setting. So how we generate this, so Bakar-Krips setting, sorry, I'll say more, I won't like, spoil you right now. And then in terms of the time analog, but on the plutonic side, this side, what we call the Archean supersuite, I think, again, like a lot of geochemists have approached it, and it looks like all these individual like suites were derived from and possibly interacted with one another from different sources at a range of crustal depths. But the most important thing, and I think many people have recognized, that the geochemical signatures tell us that we've got widespread hydrous mantle domains, at least in the northwestern UNME domain. So that was 2820 to roughly 2740. If I jump to the youngest end member of this time slice, about 2730 or so, guys like Even Zebra at JSW actually recognize a regional stratigraphic nonconformity that was a UNME-wide transition from some packages or rock succession here that you can see at the bottom of this diagram that are mostly deep marine in terms of setting. And above that 2730 nonconformity, you actually switch to totally different packages with a nice angular nonconformity in some parts, but locally just like a nonconformity, to shallow marine to subaerial rock succession marked by, you know, sandstone, siltstone, felsic volcanics. And the curious thing is those felsic volcanics, whether in Marda, in the south-central UNME terrain, or in Cosmos, in the northern Kalgoorlie terrain, they've got a high K calc-alkaline to shoshonitic affinity. So the key learning from Yilgarn 2020, if we go back to 2017, so 2017, I think this nonconformity was demonstrated to affect the whole of the UNME. And what we demonstrated during Yilgarn 2020 is that it didn't stop at the UNME theoretical terrain boundary with the Kalgoorlie terrain, but it went beyond that. And we found evidence for this nonconformity within the Kalgoorlie terrain. Now there's a PhD student, Sumaid, that finds evidence for this nonconformity at the margin of the Konalpi terrain. The question that we'd like to test is how far can we extend it? Because if we were able to extend it to the length of the Proto-Craton, then it stops being a regional feature and it becomes a Proto-Craton-wide features, obviously with strong implications in terms of the tectonic evolution. Last thing I want to mention is that coincidentally, the 2740, 2730 millionaire time slice, according to a paper by Gauss-Comonal in 2019, is also correlated with a metamorphic event that produces relatively moderate P conditions of imperceptible light associated with a tight clockwise PT path. So crustal thickening and 3 times 9 is 21, so probably in the reach burial to 25 kilometers paleo depth. Crustal shortening, burial, and then high K calc-alkaline affinity for those specific volcanic rocks. In terms of what the isotope can tell us, orogenic isotope can tell us, if you look at, again, the half muon versus age ratio, what's interesting is that from 2810 to roughly 2060, you've got mostly suprachondritic values for the felsic igneous rocks. And as of 2060, you've got an isotopic pull down, if it was like a normal, like epsilon half versus age. But in other words, like you're basically switching the suprachondritic values to subchondritic values, meaning that you're starting to rework ancient crust. And if you look at the two-stage depleted model age for that rework component, it's 3000 to 3800, which could be related to some material akin to Naria age. So the whole lot, everything that I've discussed in the last few slides, when taken collectively, actually has been utilized by Rowan al in 2022 to suggest that it was consistent with a collisional setting. So this is just the same diagram, and we keep going down in time. So this is just the two first magmatic events affecting the proto-Yilgarn Craton. And now we're at the stage where we think something happened on the northwestern UNME terrain and the Nile. The model that we propose currently is not going to be one involving, dripduction or drip, although it could be an alternative possibility. But we went with a uniformitarian model. What we propose is actually two options. In either case, I think the Q reef can be seen as a pretty linear, like back arc reef basin. Option one is that the subduction was actually at board of the Naria itself, and the Naria was part and attached to the proto-craton itself. And in that case, I think it will make the Q rift like about 250 kilometers away from the convergent margin. But that assumption, if the subduction is here, meaning that the Archean seismic province, which we don't know much about, will be actually basement to the UNME and will be similar to Naria. So in other words, basement to the UNME, that option will be Naria. In the second option is to have a subduction zone intervening between the Naria microcontinent and the rest of the protocraton, and basically crashing at around 2760 or so with the rest of the Yilgarn protocraton. And I think recent knowledge on the Naria, although JSWA is gonna start like another lot of detailed studies like over the coming years, so maybe they'll change the picture. But I think the stuff that we know, the emerging knowledge from the Naria, is consistent with a major bang happening around the realm of 2760 to 2730. So if I keep going down, after the aftermath of the so-called or recently defined Naria orogeny, we basically switch back to lithospheric extension, or lithospheric thinning, sorry, and extension of tectonics. And that's what I think most people will be familiar with. And that's the really famous 2720 to 2690 magmatic event 3, which is correlated with the Kalgoorlie supergroup and correlatives throughout the Eastern Gulf superterrain. And that's obviously famous for the phenomenal endowment in komatiite-hosted nickel deposits that is well known in the Kalgoorlie terrain. So obviously, I think the rocks of these ages are mostly and voluminously deposited like in the Kalgoorlie terrain. But I think recently there's been a lot of work like trying to define like such succession in the Yamana terrain. And we also know that there's such young succession within the guts of the southwest terrain called the Saddleback Greenstone Belt. Unfortunately, there's not much work done on it, like or the studies that have looked at the Saddleback Greenstone Belt are from the 1990s, so we really need to get back to it at some point. Irrespective, if I'm looking in the guts of the young Kalgoorlie terrain here, and I'm looking at the northern side of the Kalgoorlie terrain, what is called the Agnew-Willen Belt. This is a map that was modified from existing JSW map like during the Yilgarn 2020 project. What's curious is that throughout the Kalgoorlie terrain, due to the specific ways of emplacement of komatiite, true komatiite this time, they're commonly used as a marker horizon. But you'll see from this map that around the Agnew Dome here, we've got not only one, but two komatiite horizons. So the Agnew komatiite and the Donegal komatiite. Now, back in the days, I think most people have argued that it was the result of stratigraphic duplication, structural duplication. We know now with all the work that has been gone into it, like whether geochemical barcoding, detailed UPB chronology, or even geological mapping constraint with Younging direction and differentiation trends, that it's actually a stratigraphic feature. And there are in fact like two komatiite horizons. And during the Yilgarn 2020, we really tried to pull the stratigraphic pile apart in that belt. And this is a bit of a complex diagram. But what you see is that basically highlighted in gray is the classic 2720-2690 package, the mafic, ultramafic, like supracrustal sequences. And you see directly from this diagram that it's actually underlain by two other events of magmatism. One at 2825, 2740, that is analog in age to the Murchison supergroup, and the so-called or identified 2730 unconformity with those like felsic cosmos volcanic complex that has a high K-K-K-line to shoshonitic affinities. So again, we fall back on a fit, and we know that there's definitely something else that happens prior to that 2720, 2690 Kalgoorlie large igneous province. So what we're arguing for is that there's probably about 130 million years of magmatism that is nearly continuous with no major magmatic hiatus between 2820 or bats all the way down to 2690. Now, a brilliant PhD student like Anne Brand-Venus has published like a couple papers. This one is pending submission to Litos. And she's allowed us to confirm our interpretation, basically, looking at geochemical barcoding of every single like units recognizing the field and checking at it a bit of geochronology and detailed lithofacious analysis. Now, if we try to go beyond an upscale, basically going from the Agnew Woolen Belt and zooming out to the scale of the Kalgoorlie-Konalpi terrain, this map is actually a compilation of all the igneous crystallization age. I won't talk too much about the max depth page, but all the igneous crystallization age that are pre-2730. So to get like basically anything that is older than this sequence we've been talking about. And you can see that the spatial distribution is largely in the north-central part of the Kalgoorlie-Konalpi terrain, with very limited data for the guts of the Kalgoorlie region itself. Then looking at the edges, I think we've got a couple peaks, one peak between 2810 and 2800, another peak at 2770, 2745, and the last peak at 2740, 2730, more or less. Each peak is actually age analog to individual groups of the Murchison supergroups. So in other words, what we're arguing for is that actually you and me / Birdville is actually basement to the Kalgoorlie-Konalpi, and therefore those terrains should be better classified as a rift. If we upscale once more and look at the Craton altogether, here is a space-time chart of all the stratigraphic units basically in the you and me, the Kalgoorlie-Konalpi rift. You'll notice that the diagram is cut at 2720 more or less. So we're looking at anything that is older than the bulk of these supercrustal sequences in those two terrains, and then the Birdville on the other side. And you can see that basically what's interesting is that we can track back a shared geological history all the way to 2950. I'll argue that we can push that like definitely to 3010, the start of the oldest like Southern Cross supergroup. And the question is how far more? We haven't done the work like to know how far back basically the you and me and Birdville were part of such protocrate. Just to hammer the nail like a bit more, Smiths and collaborators at JSW actually published two fantastic reports. So one report, JSW report, in 2023, and derived from those results he actually published in Geology at the start of the year. And he's basically looking at classifying the granite systematically using obviously his geochemical skills. And what you noticed is that if you start to classify these granites, there's some northeast to east-northeast trends that are strike extensive that seem to delimit the source region for the generation of those granites. So in other words, like in the central region here, you've got low calcium granites on another side as well. And in the Q isotopic zone and in what we call the southern ISRY zone, you actually have everything else, but not the low calcium granites. And obviously the picture changes a bit once you reach the Eastern Gulf superterranean. But what's interesting is that those trends, actually, they don't stop at the theoretical boundaries, the Ida fault, which is a proposed suture. As of 2010, there was a proposed suture. Actually, those trends go beyond it and extend almost all the way to the Birdville terrain. So in other words, what we're saying is that we're imaging a northeast to east northeast lower crustal architecture that doesn't care about those terrain boundaries. And because they strike extensive and potentially depth extensive, if we map them in one data set, we should be able to map them in different data sets. So that's a key learning from Yilgarn 2020 is we used a lot of different data sets. I'm going to show you 3 here. And we think we can map those structures actually in pretty much every single one of them. So here is a Booger anomaly gravity image. And you can see that obviously there's a lot of different lineaments in different directions. But I think most people would agree that there's a pronounced set that is at a high angle to the upper structural grain of the eastern Goldfield superterrain and roughly east-northeast in trend as well. If we look at the depths to Moho, we can also see like a pronounced set of orogen oblique, Calgary orogen oblique lineaments. And if we look at data like a bit less traditional, such as the earthquake epicenter data, I think, again, there's a trend that is parallel to the orogenic tectonic zone here, the boundary between the southwest terrain and the UNM terrain. But I think most of you would agree that there's definitely like northeast to east-northeast trends that are quite pronounced as well. So the implication from all this work is that the north-northwest south-southeast structural grain that is characteristic of 2/3 of the Yilgarn Craton, the 2 eastern thirds, basically, is not the result, of accretion of exotic terrains onto the margin of the craton, but it's actually a really late overprint and essentially dominated in the upper crust, whereas the lower to middle crust actually shows an architecture that it's almost at the right angle to that late imprint during the Calgary orogeny. Now, I must admit that there's more work to be done in terms of the 3D and more importantly, the 4D integration. So we know these strands have to be formed like quite old, perhaps like as old as 2800, if not older, but there's a lot more work that needs to be done in terms of the 4D evolution. Just as a credit shot slide, we didn't invent those trends. Actually, they've been known for a while, like as far back as O'Driscoll work in 1986, and people have actually hinted at them like using a different data set. So some using stratigraphic lens, other using geophysics. And more recently, some papers like by Molna looking at it from the isotopic perspective. So it's not new to the story. We're just like trying to elaborate a little bit and putting them to the test. Now, I'll mention rather quickly that we've looked at obviously the Calgary Konalpi terrains, but there's also like the supercrustal rocks are also known from Yarmana in the far east Yilgarn margin. And there's a paper that actually added a lot of new data to really try to decipher what's happening to the east of the Yilgarn. That's Scheffel and Al 2024. He was a PhD during Yilgarn 2020. And he's basically been able to identify a narrow rift zone, which he entitled the Yarmana Rift, sandwiched between 2 older blocks akin to the Birdville or UNM in edge, which are called the Dorothy Hills block and the Birdville block. So that was for the magmatic event 3, and then I'll jump to perhaps the most interesting time slice for most geologists out there, the Calgary orogeny, which supposedly started between 2675 and ended around 2630, although that's debatable. It probably could be pushed like a bit to younger times. And the reason why we love it is obviously because of the gold endowment that is correlated with. So Yilgarn 2020 team actually went at revisiting a bit the structural framework. When you talk to structural geologists, there's basically 2 groups of people. There's the lampers, most likely Europeans, and I pled guilty to being part of that crew. And then there's the splitters. Yeah, and then if you push it too much and you go beyond D10 in Precambrian terrains, I think you're probably part of the group that is called dementia or something else. But irrespective, what we try to do is to just revisit the structural framework of the Calgary terrain with a totally different vision, basically. And the diagram is going to be a bit complex to explain, but I split it in 3 parts. So the start or the onset of the Calgary orogeny, we believe, is roughly around the 2675 mark. The youngest gabbro seals in place in the mafic ultramafic sequences fall in the mark of 2687, 2685, depending on where you look, southern Calgary terrain or northern Calgary terrain. And there's also the onset of the Calgary orogeny is also correlated with the peak in high calcium granite at 2675 more or less. And those high calcium granite, they actually typically they have a high SR-Y ratio, which means that they could be interpreted to have melted from an unrich and or deep source. As we move towards younger time, 2675, start of the Kalgoorlie orogeny, it all started with a period of east-northeast, west-southwest directed horizontal shortening. Key things that have been developed during that time slice is actually amphibolite to granite facies gneissic layering, the peak in high serre granites, we just touched on it, and tied to isoclinal recurrent F1 faults. Coincidentally, I think we tentatively link this period of this early increment of deformation, frosting and recurrent folding, to a metamorphic event described in Ghost Comunal in 2019 that is a low P, high T relic paragenesis that have been identified along crustal scale structures across the Eastern Goldfield subterranean. Now there's a second increment of deformation. We consider the two to be progressive, actually, instead of like polyphase at distinct times. Also marked by no change in far-field boundary stress condition. It was linked to granite doming, F2 upright folding, exhumation, and ultimately molasse deposition. And in the Yilgarn Craton refer to these sequences as late basin. This event of deformation was linked to what we call the metamorphic 2 event, which was low P, moderate temperature, and associated with tight clockwise PT paths, so crustal thickening, and dated at 2672 plus minus 2 by Goscombe using metamorphic monazite and zircon. Sorry, I forgot to mention that the key thing, the key argument for the evidence of this progressive increment of deformation is actually the angular unconformity that we consistently see at the base of the late basin. So we know there's been an increment of deformation before deposition of the late basin sequence, because we know that at their base they've got this angular unconformity. Now, the key thing to distinguish D1, D2 from the rest of the deformation increments is that actually you deposit those late basins and then you affect them with deformation AI, you invert those late basins themselves. So again, a major difference maybe with some of the work like published earlier is that we still see this D3, D4 increment of deformation as part of the same progressive deformation with no change in far field boundary stress conditions. But we invert those late basin sequences and then we switch to a strike slip dominated transgressive system. And we tentatively correlated D3 and D4 with two metamorphic events like pinpointed in Ghost Comunal, M3, low P, moderate T. The only thing that's changing from M2 is actually a bit of a thermal anomaly where you keep the pressures roughly the same, but you've got a little increase in the temperature, most likely due to the switch from high serre granite to the low calcium granite around the 2660 mark. And this event of metamorphism was dated at 2656 plus or minus 3. And then there's a late event that is called M4, where you basically lower the pressure and lower the temperature, tight clockwise PT pass again, but dated in two little peaks, 2645 and 2630. So exhumation and moving towards cratonization. Now, just to say a little bit of something about the metamorphic constraints, I think that's a key thing for future work is that there's only a limited number of studies that have actually integrated structural, metamorphic, and geochronological data, therefore achieving what we call like a complete record of the PTTD path. Now, if you look at Ghost Comunal 2019, I think that's probably one of the key studies. All the events from MA to M4, they're basically in time spanning the Kalgoorlie orogeny. Forget about M1 because it's linked to the earlier event, what we call the Nari orogeny. But if you look at the max pressure condition, they're in the realm of 7. And if you were to take this Pmax actually at the peak temperature, they'd be even lower at 5 kilobar. Altogether, I think the 6.5 mark is roughly equivalent to 22 kilometers paleo depth. So some people would argue that there's actually been only minor burial during all the crustal thickening associated with the Kalgoorlie orogeny. And I think that contrasts like quite majorly with colder Proterozoic orogens that are usually marked by higher P moderate T conditions. Now, having looked at the Kalgoorlie terrain as a whole and proposing a new structural framework, we wanted to test for upscaling. And the way we see it, like we believe that the structural framework we've seen in the Kalgoorlie terrain, which by far I think has been the best studied terrain of all the Yilgarn Craton over the years, we argue that the stuff that we record in there is actually the reflection of the Kalgoorlie orogeny imprint on the rest of the Eastern Goldfield superterrain and potentially on the whole Yilgarn Craton. So we've set up a little map looking at digitizing all those faults and shear zone using a mixture of geological maps and geological interpretation of geophysics. But what you can see, we've got a distributed crustal shortening and transpressional shearing that is more or less characteristic of hot orogens underlain by weak lithosphere. And if I try to sum it up, like I would say that the north-south striking features are actually down deep slip. The northwest to north-northwest record sinistral slip, and the north-northeast feature actually tend to record dextral slip, which altogether suggests that basically 3D belt terrain was accommodated not only by orogen parallel shortening, but also vertical stretching. And more importantly, I think that we have a case to argue that the bug geometries and deformation modes that we see as in the Yilgarn Craton are actually akin to some documented or reminiscent at least to tectonic processes in modern hot orogens formed in modern plate tectonic regime. Now, this is just a bit of a sketch of the way we see things, and a model that we propose in a paper that is now accepted in Precambrian research. So remember, we had this first bang bringing Naria onto the UNME, or just inverting the Q rift if the subduction was at board of the Naria, still stuff to be unraveled. And then the proposition we make is that usually in Phanerozoic Earth, when you close subduction one way, you either change the polarity or you transfer that subduction elsewhere. Well, we argue that after 2730, subduction actually switched to the other side of the Yilgarn Craton, still west dipping, but we mostly are in a retreating stage that thins the lithosphere, open up what is known as the Kalgoorlie-Konapi rift. And I think this way you can reconcile the fact that there's a plume or a little mantle upwelling, perhaps coming from the mantle transition zone 410 to 660, responsible for voluminous outpouring of very primitive mafic ultramafic magmas throughout the Kalgoorlie-Konapi rift. And then when that subduction zone dynamics change a little bit and you switch back to contraction, then you basically start the Kalgoorlie orogeny. That's when you have like deposition of those black flag group and correlatives, the peak in high calcium granite. And as you keep going through the convergence until about 2665, which we think, we hypothesize, is the timing of the collision, based on the fact that it marks the onset of late basin deposition. It's also the timing of the activation of the corrosion tectonic zone, is the switch from the high calcium granites to the low calcium granites. And it's also the timing of a recent discovery of intrusion-hosted nickel copper PG at Julimar, here, not too far from the Perth Hills. And then when you have finished all that stuff, basically you're moving into a strike slip dominated system, and the bulk of the gold kicking in into largely the eastern Gulf super terrain, but also the rest of the Yilgarn Craton. Now, to jump into the metallogeny, because that was the second part of the talk. Basically, this is a picture from Molenal in 2019. I really like it because he puts perspective into a lot of things in space and time, divided into the West Yilgarn, basically the Proto-Yilgarn, and the Eastern Gulf super terrain. And we'll mostly focus on the gold metallogeny. I could talk about many other things, but I think Yilgarn 2020, to be fair, focused largely on the gold metallogeny. So we're going to talk about this time slice, so the Kalgoorlie orogeny. But just before I get into detail about that, I'd like to mention something that I think is quite interesting. If you look at that time slice between 2705 all the way down to 2600, more or less, it all started with komatiite-hosted nickel around 2705, like coeval with eruption of those voluminous primitive mafic ultramafic sequence. Then slightly younger in time, although you can argue that some of these VHMS deposits are actually as old as the 2705 mark. Between 2690 and 2680, we got VHMS to cite like a few Teutonic Board, Jaguar, Jungle Pool, Nimbus. Then we moved into the realm of orogenic gold, or not so orogenic, like we discussed that down the track. Then at 2665, we've got the intrusion-hosted nickel copper PG, which for us marks the timing of that collision closure of that subduction zone. And then obviously we also move into the realm of lithium pegmatite, although there's a question mark in there because I don't think we've got much geochronological constraints as of yet to really pinpoint the exact timing of when the lithium kicks in with respect to the rest of the story. Now, when you consider this sequence of mineral systems in space and time, there's a beautiful paper by David Houston, GA, and collaborator that just got out in Earth Science Review in 2023. And that's what these guys call actually a convergent margin metallogenic cycle. Yeah, and that's something that we see in the superior, we probably see in the Zimbabwe, and if we were to look for it, I put a bet that we were to see it in most Neoarchean terrains. So jumping the gold metallogeny, here on the left-hand side, you've got a picture from a PhD Ravish Raffle submitted to geology like just in the last couple of weeks. And you've got like a distribution of the minor, medium, and major gold deposits. And on the right-hand side, you've got a map of the hafnium, epsilon hafnium plotted in space. Be careful that the color actually, like it's a bit of the reverse traditional color. So the reddish color, the hot colors are actually the more juvenile stuff, where the bluish is actually the older reworked crust. But a key relationship is that in terms of the spatial relationship, you can see that the bulk of the gold, with a few exceptions, like one being Boddington, are literally plotting spatially. They're located in the zones of anomalous juvenile mantle-derived material. Yeah, so the Q rift, Calgary Canopy Rift, and the Yamana Rift. So in other words, like in terms of terrain selection, I think what he says clearly is that you need to prioritize like back-arc rift basin with the youngest and most significant pre-inversion juvenile input. Now, in terms of a bit of the evolution of thinking in terms of the gold metallogeny itself, is that I think there's a number of papers now that have recognized that gold happen in distinct pulses throughout the Calgary orogeny. Now the debate remains like mostly around the nomenclature, not so around the age, because some of the early golds like should not be called, I think, orogenic. If you take the definition of David Groves and all, like in 1998 or even the 2030 gold file. So multiple discrete gold events. Obviously, there's a lot of diachronicity at the camp scale and even more at the terrain to Craton scale. So it's a bit hard to pin them down into groups, but I think most people will agree that there's an early gold group and then a late gold group. And the early gold group dates that we currently have, it's probably anything spanning from 2675 all the way down to 2655. And then the late gold group spanning 2640 all the way to 2630, more or less. And the current emerging view is that the early gold group is actually more akin to magmatic hydrothermal deposits, whereas the second group is actually more akin to proper orogenic gold, whereby the source of freeze and metals is linked to metamorphic devotization. To make a case like down to the deposit scale, so we're going to look at the giant golden mile deposit, about 60 million ounces in the southern Calgary terrain. And basically, there's been fantastic work done by a PhD student, Jordan McDivitt, in 2022, published in Economic Geology. And he really he threw everything he could like at dating the pulses of mineralization using UPB shrimp geochronology on pre-scene and post-ore dikes. He also combined those results with hydrothermal dating of xenotim, zircon, titanite, and apatite. And when he just puts all the stuff together, he was able to actually split the structural pargenesis in terms of 3 gold pulses, the oldest one being linked to Fimiston Hidden Secret, that is at 2675, the second one that is called Oroya at 2665, and the youngest one, the Mount Charlotte Stockworks at 2640. So here again, evidence for a pulsated, like a protracted gold mineralization event. 3 different pulses recognized only at the giant golden mile. And I think some people will argue that the only reason you have a giant gold deposit is actually linked to the superimposition in space of different gold pulses, like linking to progressive upgrading of the bulk tonnage and grade. No, because we recognize that the early pulse of gold is probably linked or it's got a bit of a magmatic affinity, part of the Yilgarn 2020 team led by Chris Fisher and Tony Kemp actually looked at the fertility aspects and they make a case. Actually, one of the key learning is those zircon apatite fertility indicators that work, actually demonstrably work in Phanerozoic arc for Phanerozoic arc magma, seem to actually have like strong potential and appear to work in Neoarchean origins, such as the Calgary origin. So I'm just going to show not going to show the zircon results here, but I'm going to look at apatite. And the reason I'm doing that is because for those of you who've worked in trying to date zircons in Archean terrain, like they're often radiation damaged, fractured, altered. So it's more often a miss than a hit. In contrast, I think the apatite is typically much better preserved. It does not accumulate like radiation damage as much. It's quite resilient to alteration. And the most interesting thing is that it's nearly ubiquitous in igneous rocks that somehow, even those that will be zircon deprived, such as mafic, ultramafic lithologies. So on the map on the left, you've got the barren suite that are represented as dots. and you've got the fertile suite as stars. Now the fertile aspect is basically linked to the fact that we've got mineralization overlapping with magmatic ages, or the fact that we've got high temperature mineralization assemblages. And if you look at the result, the diagram showing the results here, it seems that the fertile suites are actually the suites that fall in that little square box that have strontium more than 1,000 ppm and yttrium about less than 1,000 ppm. And what they reflect is basically a proxy for the hydration state of the magma, because high strontium actually is basically a proxy for plagioclase suppression in hydrous magma that ultimately leads to higher strontium content in crystallizing apatite. And just because I think time is running out, I've talked for a while now. I just wanted to say that if you've liked some of the results presented here today as part of the Yilgarn 2020 initiative, there's been a follow-up collaborative research project that is trying to get up and running. The core team is going to be extended, not only just UWA, but now the UWA CET, the newish center that is called the Industrial Transformation and Training Center that is being set up by Marco Fiorentini at UWA, Curtin, and the University of Sydney. And we've got quite a great multidisciplinary team of great scientists across those different institutions. And the game really is to try to bridge the gap between terrain selection and camp scale exploration strategies. And what the Yilgarn 2030 collaborative research project offers, I think, is a novel scale-integrated multidisciplinary approach to improve our predictive capacity for targeting for a range of systems. So it's not going to be just about the gold. We're trying to extend to all other different mineral systems. So nickel, copper, PG, lithium, rare earths maybe would be part of it as well. And the 3 core modules that are currently being proposed are listed hereafter. So mapping the translithospheric corridors to follow up on work initiated during Yilgarn 2020. And essentially putting a lot of emphasis and focus on mapping the 3D and 4D evolution. And then also trying to validate those ones, like either in the field or through numerical insights. The second module is going to be about mineral systems. So it's basically dating the metallogenic record, extending to other mineral systems to link it and test the tectonic evolution like proposed throughout Yilgarn 2020. You're also going to include like a structural perspective on LCT pegmatites, because I think like when you look at the system, it's been vastly dominated by geochemists and isotope geochemists, and there's a lot of work to be done like in terms of structural geology. And there's going to be another module following up on those alkalic, so cyanide group, and calcalkalic, the sanuclitoid or Myfi group, copper gold system, because they're a bit exotic to the Yilgarn Craton. And there's a lot more work that needs to be done in terms of deciphering the genesis. And then the module 3 is going to basically integrate it all. So therefore the name, and it's going to try to look at it from a visual perspective. So creating a geodynamic atlas that's going to try to animate in space and time all the magmatic suites, sedimentary series, mineralization ages, metamorphic constraint, and so on. Second thing, that's going to look at the granite geochemistry, but in a visual way. So you know that when you plot like a bivariate element or ratio like element ratio time diagrams, like the spatial and temporal trends are hard to decipher. But if we were to actually plot that geochemical data as a function of time and space, then we could use it to prescribe fertile areas for a range of mineral systems, such as gold and lithium. And the last thing we're going to do is to use the legacy drilling data from company and proprietary bottom-of-hole geochemical data, and to try to set up a semi-automated approach to recognize protoliths and alteration types and intensities. And we'll start this at deposit to camp scale, I think, and then we'll try to test if it works when upscaling. So if you're interested by any of that, please get in touch, and I'll be happy to give you a bit of a pitch of what it is that we intend to do, why, and how. Otherwise, thank you, Jess, and thank you everyone for listening. And I'm open to questions, I guess.
Thank you so much. That was awesome to hear from you. So thanks for taking the time to chat.